So next I will talk about the SRIM software. And this is now in a way less scientific part of the lectures, but this is very important to know about the SRIM software and what it does and what its physical limitations are. First of all, the reason we bring up SRIM now is that it is one of the two best sources for electronic stopping data. So SRIM is, in addition to being a software, is also an organization called SRIM.org, this SRIM here stands for the stopping range of ions in matter. Originally it was called transport range of ions in matter, TRIM, but in the last about 20 years the name has been SRIM, and most people have switched to using the word SRIM. And the reason this is related to electronic stopping is that there is a major collection of stopping data is available at the web pages of this organization. And this is also quite well documented. There are several publications, there is extensive material on this website, and there are two books. The original so-called ZBL book by Ziegler, Biersack and Littmark is from 1985. And now there is a more recent book published by the SRIM organization called the SRIM book simply, which actually partly overlaps with the ZBL book, but also has newer stuff in it. Then there is another organization which is completely independent, which is actually a United Nations organization, the International Atomic Energy Agency, IAEA, and they have also a stopping power database which is independently maintained. And this is very important that in case something happens to the SRIM organization, the IAEA will certainly still be there as long as the United Nations exists. So before we go on to actually how to use the software, I'll show that some of the data is available, the examples of some of the data available. So this is examples of data available on carbon. And you see here each letter here is a data point. So you see that there is a huge amount of data available. So this each letter is the ion, and then or name of the element is the ion. So for instance, helium, this would be helium ions in carbon, that would be a nickel ion in carbon, this would be a lithium ion in carbon, and so on. And as you see, there is some variation there, which is after a normalization procedure. And here you see that this variation is compared to this SRIM stopping model from 2011. Also, these SRIM stopping models, the SRIM software enables giving and using a numerical theoretical calculation, the stopping of any ion in any material, and this has different versions from different years. So this also somewhat complicates this. There isn't typically a huge variation from one year to the next few percent or less, but except that sometimes some energies may have a bigger difference. But anyway, you see that this is a comparison to the experiment versus the theory, and here you see that there is considerable variation. The mean error is 6.7%, so this means that the model stopping powers are not perfectly reliable. On the other hand, you also realize that the experiments are not fully consistent either with each other, so there is some uncertainty, and roughly speaking, one can say that the order of the uncertainty of the SRIM stopping powers is plus minus 20%. Well, this is another example for copper. You see that there is a huge amount of data available for copper, but then not for every system. If I target samarium, which is of course a much less common material than copper or carbon, see that there is also much less data available, basically just a few data points. But this solid line, the SRIM model, works for all cases. So this was the importance of the SRIM website as a source of stopping powers. Um, and But the SRIM is also a software, and as I said, it's nowadays called SRIM, but originally it was called TRIM, and this name TRIM lives on in some branches of the software, which were then independently developed by others. So what does SRIM do? First of all, it has two operation modes. One is to calculate any stopping power, electronic or nuclear, in any material. And this includes compounds with arbitrarily many elements, multi-layers, and so on. So it is quite versatile in this. But keep in mind this, that there is this plus minus 20% typical uncertainty, so it's not perfectly reliable. But the other mode is that it can simulate ion ranges explicitly based on the so-called binary collision approximation. This approximation will be described in the next chapter on the course, chapter 4. And it always includes the electronic stopping in all of its calculations. But the physical limitations are the key limitation, usually the most biggest one, is that it cannot detect crystal structures at all. So it has absolutely no description of channeling effects or any other effect related to crystal structure. And this is very important to realize, because sometimes the crystal structure is very important. Well, then it only works on Windows computer. It's not open source, and it's apparently still programmed in a version of Visual Basic, which was a popular programming language in the 1980s when they started working on this. But nowadays, very few people would use Visual Basic otherwise anymore. And unfortunately, because of this, installing it on Windows computer, modern Windows computers, is actually somewhat of a hassle. I managed to install it on Windows 10, but basically you have to read the advice very carefully. And one thing is, you're not living in the United States. You have to set regional settings to US English, because otherwise there is a really weird font problem which makes it practically unusable. But now I'll give a few slides of how it looks, and then there is a video demonstrating it. Actually, that's a video within this video. But okay, so you start the software after you installed it, and then you have get an opening menu like this. Here you can, if you want stopping powers, then you click here, stopping range tables. If you want a simulation, then you click trim calculation, and then you see that you can also get access to the experimental stopping power, and there is some background information here. These plots are shown for SRIM version 2013. So there are many versions from different years, and there is also a newer version by now. And as you can see from the years here, it's been around for a while. They say that the first copyright on the first version, which was not graphical, is from 1984. These first versions were fully text-based. But anyway, if you then actually want to run a simulation, you get a screen like this. Then you can select the ion and the target atomic name, and then when you are done, you click here, save input at run trim. Notice that it actually here says run trim, even though the software is called SRIM. And then when you start running, it starts running, and you start getting quantities like the mean range is shown here. In this case, it was 1,320 angstroms for 10 kV hydrogen ions in silicon. Where was the? Yeah, here it is. Here the element is said. Here is the ion is shown, and then there is the energies there, and so on. And then you can also get a number of analyses like ion ranges and recoil distributions, energy to recoils, damage events, and so on. One notice is that the energy to recoils is pretty reliable if the material is amorphous. This damage event is problematic, and we'll return to later on this, that this so-called damage event analysis in SRIM has is somewhat confusing in that different SRIM modes can give different results. And now here is a video of running this, and now note that this video is independently available on YouTube. But now I'll run it within these lecture notes, and so what you'll hear now in the next moment is my voice from the video.
So this is a video demonstrating the use of the software SRIM. So this assumes that the SRIM has been properly installed at the Windows computer in advance. So if it's been installed, you start the software as usual. Then if one wants to do an actual simulation, select SRIM calculation. And here one can select the modes on the top, but in this case we'll just do a very simple calculation of boron implantation at an energy of 30 kV into silicon. We have selected boron up here and silicon up there. Then what you may want to change is the layer thickness, but we'll now start with the default values. Note it's possible to also change other parameters here, but right now for this example we don't change anything else. When you click Save Input or Run SRIM, you start the simulation of the ion trajectories in SRIM. And as you see now, most of the screen is empty, so it's we don't get very good information, but it's possible to change this plotting window resolution. So now we see that everything happens about in the first 2000 angstrom, so we can change it instead of 10,000 to take in the top 3000 angstrom, and then end edit and restart, and then now you see the trajectory is better. And as you see, there is a number of information which is given, like mean range and so on. It's also possible to get stuff like the range profile directly during the plot. One hint is actually also that this is slow because all this plotting takes time. So if you want to speed it up, you can just remove all the plotting windows. And then again, if you want to follow the ion distribution, you can click this and see how it's developing. The final thing I'll show now is that it's possible also to take this more detailed full cascade mode calculation, and then with this one can get a much more detailed information, also the trajectories. But do note, as explained in the lecture note, that this SRIM has many limitations, and some of these quantities should be viewed with great caution. Like the sputtering yield, for instance, is very sensitive to the SRIM parameters. But this was a brief video introduction into how running SRIM looks. When you're done, you can stop your simulation, pause SRIM, and then you can get also data files of the quantities you need onto your computer, and so on.
Okay, so that was it, and I hope from this double lectures on this SRIM you get an idea of how it works. I realize now in this video the top of the SRIM window for some technical reason is not shown, but when you run it, it will be quite obvious what the options are up there. And here is some notes which are actually already said that, yeah, you can speed it up by closing all output windows, and you can run it in the background on multi-core computers and run keep doing other stuff in the meantime. And you can get many output options, and you can actually get all the collisions in the simulation by selecting to output a file called collision.dat, which becomes quickly a quite big file, but from that it's possible also to do further analysis. But yeah, I really emphasize that in doing science or technology, you should know what you are doing. And there are major caveats already. The sputtering yield was mentioned, the fact that the damage event calculations are not fully consistent, and channeling is not included, and there are others. But actually, the good news is that if you go through this course, you will learn about all the physics which is really involved, and we'll also mention a few times how far SRIM can go in describing this. And this was actually this part of the lecture notes. Next, we'll finally go to damage from electronic stopping, also known as ion track, which is one more exciting topic.